In this final movie for this part of the course, we're going to be completing this terrain project that we started a few movies ago. And let me just press play to see where the stage that we're at right now. If I press play on the toolbar, I can move the capsule forwards and I can move it back and I can move it left and I can move it right. And not only that, but as I move it forwards, again, the object is moving up and down vertically to match the horizontal or to match the vertical alignment of the terrain. So as the terrain elevates and as the terrain lowers, this capsule is going to move up and down to match that. But one of the problems that I want to highlight, one of the things that's currently missing, is that as this capsule again increases to match the height of this hill here, notice that the forward vector is constantly pointing forwards. And what I want to do is I want to rotate and orient this capsule to match up with the inclination of the terrain beneath. So at this stage, for example, we should in fact have this capsule rotated like this to match up the inclination of the terrain underneath. And then as this capsule passes over the top here, again, the orientation should change to maybe something like this to match up with the inclination of the terrain that's below. And this capsule should always constantly maintain the inclination of the terrain that's directly beneath it. Now, to handle this, we're going to be relying on the concept of normals. So to illustrate this, I'm going to change temporarily the shaded mode of the viewport here. Right now it's in standard shaded mode. I'm going to click on that drop down to pick shaded wireframe to change the shading of this wireframe terrain here. So what you can see is the tessellation and the polygons of the terrain in rows and columns and their edge loops. Now, when we're performing the ray intersection in our code, we are casting a ray downwards from this capsule object down into the terrain. This will intersect the terrain at a particular point, and it will intersect a particular face. Now, each of these faces on the terrain will have their own normal. That is a vector that is sticking out of the center of the polygon and indicates the direction in which the polygon is facing. So for example, this polygon here that is at an angle will have its normal vector pointing outwards to match the inclination of the surface. And each of these polygons will individually have their own normal indicating the orientation of the face. What I effectively want to happen is for the ray that we project downwards to intersect a particular polygon, and that polygon is going to determine, or rather the normal of that polygon is going to determine the orientation of the up vector of this object, so that the up vector of our capsule will constantly maintain and change to match the normal of the polygon that we intersect beneath. So I'm going to switch this back to shaded mode and get started at coding this. So I'm going to switch back to, again here, our hover folder, and inside the terrain hover script, I'm going to double click on that to open that inside MonoDevelop here. So we have our hover script. Now, what I want to adjust first of all here in this hover script is we need to find out what the normal is of the polygon that we intersect. Now, to record that information, I'm going to add a completely new variable. It's going to be a private variable because I don't need this to be visible in the object inspector. So I'm going to create a completely new private variable here called private vector3, and I will call this dest up, and it's going to equal vector3.0 as an initial value here. Now inside the intersection, I want to record inside dest up the normal of the polygon that we have intersected. So I'm going to choose dest up equals hit dot normal, and we can record that normal data inside the dest up variable. And then finally, after we have set the position of the object, I want to update its rotation using spherical interpolation to gradually and smoothly change the rotation of the object over time to match up with the dest up vector. So I'm going to choose this transform dot up to set the up vector of the transform component. And I'm going to use vector3.slurp. Now notice, just like quaternions, vectors also have a spherical interpolation function. So I want to match up the up vector of the component, and I want to rotate it to match the dest up vector by a particular speed. Now temporarily I'm going to create a new variable to define the angular speed of the object, which I will call angle speed. And I will give that the speed, well, let's say the speed of 5 degrees per second. And I'm going to use that speed to rotate the capsule here. So time.delta time. And I'm going to press Ctrl S to save that code and return back to Unity here to test this out. So here again, the code is compiled. I'm going to press play on the toolbar. And this time notice that the orientation of this capsule is changing. And as I move over this hillside, again, the orientation is going to change to match that incline here. So you can see that this is now orienting to match that incline. And even as we go over the hill, still that inclination is being maintained. And things are looking splendid here. That is looking excellent. And we've seen many mathematical principles applied together at work in this simple terrain scene. And that completes the end of this part. I hope you found it helpful. This has been 3dmotive.com. I've been Alan Thorne, and I can't wait to get stuck in to the next part. See you there.